I have a personality that when I was a student and even as a teacher, it's I didn't want to just do well. I wanted to do better than everyone else. I wanted like my 100 to be as far away from everybody else's score as possible. So it's like I couldn't just get the 100, everybody else had to fail. Like that's how it had to be. Like, it had to be like I am so much better than all of you. And it's a terrible way to be, but you know, like it's my chosen profession. So hopefully there is a little bit of pride associated with it. You know, a desire to achieve things like that. You want to be good. If you're an athlete, you want to be the best one on the field or on the ice or whatever. It goes in all walks of life. If you're just content being middle of the pack, then you know maybe you'll have a really happy life. I don't know. I haven't tried that out yet. It sounds like it would be good. Um, but yeah, even as a teacher, it's like I get a good evaluation. How'd everybody else do? Oh, you all got good ones too? Ah, all right. All right, I just got to work harder. That's fine, you know. So, but this is going to tell us how we relate to one another. Relative standing, measure of position, they all mean the same thing. We talked about things like z-scores and percentile ranks. When you took those standardized tests back in the day, I remember the ones where like you went into a room, usually the cafeteria, and you took a test, and it didn't impact your grade in any way. You didn't know why you were taking it, you just took it. But you were in third grade, so you took everything seriously. It's like, oh, I would really want to do well. By the time eighth grade rolled around, you're like, oh, I don't really care about it. This is the fake test. That doesn't matter for anything. And then you find out that it did matter for something. That's why you're like in a remedial English class. And you're like, oh, I should have took that one seriously. But um, but yeah, you get the report back. It didn't tell you what questions you got wrong. It didn't tell you what you need to work on, anything like that. It just gave you a percent aisle. Yeah, it was a thing. It was like it said 99 percentile. I was like, I got the percent part. I'm good there. Does that mean I got 99% of the questions right? Like I don't feel too good about that. What happened with the last percent? And I don't remember taking 100 questions here. So like, where are these numbers coming from? Turned out that well, it was better than that. It was better. You know, I was like top tier. It was like I did better than 99% of the population. That which fed into my ego beautifully. So it's like, oh, whoa, so that puts me in numero uno status. I'm like, all right, now we're talking. But you know, like I could be tied with like 100,000 other people who are also in the that top level. But yeah, it's talking about the percent of the population that is below a particular score. So I was better than 99% of the population in math. You know, English different story. Um, Microsoft Word didn't exist back then in its current form, so I couldn't rely on the red underline, the green underline, and the blue underline to help me out. So it was a complete and utter disaster. Um, but yeah, so that's one way of representing an individual's position within a data set. You could also talk about things like z-scores. Z-score is the number of standard deviations you are away from the mean. So I am one standard deviation above the mean. I'm two standard deviations above the mean. I'm 10 standard deviations below the mean. You know, so it all depends. Sometimes you want to be above the mean. You know, like points scored in a basketball game. Sometimes you want to be below the mean, golf score. You know, because you want that score to be as low as possible. Right? So there's all sorts of different possibilities. Um, Something a little bit more morbid, I guess. Infant mortality rate. I don't think you want a nice high number for that. That's terrible. You want that to be as low as it could possibly be. So there's all sorts of different ways to analyze data. But again, you get an 80 on a test. It's like, is that a good 80 or a bad 80? Well, it depends on how everybody else did. All right, depends on how hard the test was. Depends on the quality of instruction. Depends on a lot of things. But if you could figure out where you stand in relation to other people, then you can start to flesh out what those underlying characteristics are. Right, and so that's the importance of this topic. Probably the most important topic because it has embedded within it the concept of mean and standard deviation. Right? So the empirical rule is based on something called the normal distribution, and it tells us well, it tells us what it tells us. 68% of the data lies within one standard deviation in the mean, 95% within two standard deviations, and 99.7 within three. About. So we give a 2%, a bit of wiggle room, 2 percentage points. So anything within 2% of these numbers is going to be okay. Because in statistics, as much as we want it to be, nothing is ever exact. It's exact if it's a made-up question, right? Let's just put it that way. You know, some fictitious question, and you'll know it's fictitious because the word problem will say something like, "Joe's driving down Statistics Boulevard," you know, in probability town, something like that. So, if it's something like a Gallup poll or the driving one. What is it? National Traffic something or other. I want to say NTSB, but that doesn't feel right. Something like that. But if it's like a reputable source, then it's going to be real, and the numbers are going to be ugly. All right, and so we just deal with it. All right, right smack dab in the middle of a normal distribution is the mean. And we're still working with samples. A true normal distribution would really be centered around the population mean. But what we're looking at is a sample that follows a normal distribution. So the shape of the sample is normal. All right? And this process will flesh that out for us. If I go 1 unit in each direction, the units are measured in standard deviation, so the 1 unit is 1 standard deviation. So the first one is x bar plus 1s, and x bar minus 1s. The area contained within that curve on that interval is going to be about 68% of the available area. All right. Calculus people, I know there's a few. So if you don't have any experience in calculus, it's not going to make any sense whatsoever, and that's okay because it's not calculus. This is not a math statistics course, so anything that I talk about related to calculus is not going to be on the test. It's just to add a little bit of perspective. So if you have a little bit of experience with integral calculus, so Calc 2, you learned antiderivatives, you learned area under a curve. That's this. All right. So the total area under the curve would be equal to 1. The integral going from whatever this amounts to this point, so between these two x values, underneath this curve ends up being about 0.68. So that's where the relationship comes from. So these relationships are actually built in calculus, but they're kind of streamlined, kind of like a physics class. If anybody's taken a non-mathematical physics class, you know, like fundamentals of physics or something that's just basically formula-based, you know, like where the formulas come from, they came from calculus. Where the formulas here come from, they came from calculus. Right? So if you have any experience with that, you know what I'm talking about. If you don't, then like, oh, he's still talking about it. Cool. So go out 2 standard deviations, and now you're going to capture about 95% of the data. I made this line a little too long. That's going to get us, I'll do it on the outside, about 95%. And then if you go out 3 standard deviations, and I'm going to extend my curve a little bit because it doesn't end at 3 standard deviations. But that's going to give us about 99.7. So almost all of it. So if your data works out so that you have about 68% within 1 standard deviation, about 95% within 2 standard deviations, and about 99.7 within 3 standard deviations. Then again, you get plus or minus 2 percentage points to work with. So anything between 66 and 70, anything between 93 and 97, anything 97 or better, 97.7 or better, is going to satisfy the empirical rule, and therefore tell us that what we're looking at is a data set that is roughly normally distributed. Nothing will ever be exactly normally distributed, and that's because the normal distribution concept is based off of approximations. So the numbers themselves that we're using as benchmarks to determine normality, they themselves are approximations. So how could you ever have something that's exact if its foundation is approximation? Right. So that's the theory behind it. There, I think it's in my Unit 2 packet where if you do have an interest in the calculus of it, in the Unit 2 packet, once I give that out, I give the equation for the normal curve, and so you can actually play around with the integration and see how this works. The good news is there are functions built into the calculator to account for this stuff too. All right. So the first thing we need to do is visually determine whether the following distribution is normal. All right. So we can do that a few different ways. One way would be to actually create a graph, but since I haven't gone over how to create graphs yet, that wouldn't make much sense. The other way would be to actually look at the data itself and see if it follows that same model. And basically what this is telling us, we're looking at a curve that peaks in the middle. So it starts low, peaks in the middle, and then ends low. Look at the data set. Does it start low, peak in the middle, and end low? Yeah. All right, so seems normal. And you could just state that, just some sort of justification. So low, then high, then low. You know, words to that effect. I'm not looking for anything too fancy. Nothing too fancy. Movie reference? No? I'll give the whole quote. That's all right, R4. Nothing too fancy. Now? Which one? Star Wars. That's the best one. Actually, you're not far off. Episode 3. Lock in place. This is the opening scene when Obi-Wan and Anakin were in the Jedi Starfighters. Unfortunately, the Obi-Wan Kenobi movie is permanently on hold. Unfortunate. I don't know what it's going to do. I was looking forward to that one, but because the Solo movie bombed, the Han Solo movie, they put the Boba Fett movie and the Obi-Wan Kenobi movies on hold. It was a dark day in the can house. although I watched the Solo movie again last night, I don't see why it bombed. I thought it was fine. That's well. They said that there was a boycott that was going to happen. Yeah, I didn't boycott. I mean, I'm not a follower like that. But it's like if it says Star Wars, then I'm going. But yeah, that last one turned me off big time. And now they say that the next one's going to have like a 5-year time gap, which means that they're really locking in that last movie. That's very frustrating. Okay, so now we actually need to. So we, it'd be nice if the problem is over. But it's not. Verify using the empirical rule. That's actually not that bad. It's calculation intensive, but not in a difficult way. So we just need to figure out all this stuff, which makes it seem like it is a difficult thing. Let's get the data in, L1, L2. Definitely quit out of here so I don't lose my program. Stat, edit. Highlight your column headings, hit clear and enter to wipe them out. And then start typing away. Oh. Food. Double checking my data entry because number one source of error in statistics, you're looking at it. Data entry. All right, so stat, calc, 1. The settings that we had in there previously should still be there, so you should be good to go. Go right to calculate and hit enter. All right, so this is the information that right in this main screen here is what we need. Snippet, ooh, edit, paste. There we are. All right, so we need this file. This file, oh, I don't need shapes. All right, so we have to run all these calculations, but we may not need them all. Maybe we just need the first calculation. Just in order to be a normal distribution, you need to satisfy each of these 3 percentages. If any one of them fail, then it's not normal. So if it's not within the 66 to 70 interval for the first one, then you stop. All right, so maybe there's not a lot of work to do, maybe there is. All right, but we still have to do it. Now, it's up to you which way you want to go. If you want to actually start typing in values and roughly crunching the numbers. I don't like doing it that way, but you're starting to get a sense of the way I like to do things at this point. And it's not always going to be the way you want to do it. It's almost never going to be the way you want to do it. So the way I'm going to do it is to go into my vars menu. And if I'm a rookie with this calculator, I'm definitely going into my vars menu because I want to try to build some familiarity. I want to build some muscle memory with this calculator. Vars, option 5. Numbers 2 and 3 are the ones that we need. So 2. Unfortunately, there's no way to select 2 items in a list at the same time. That's annoying. But I'm going to write x bar minus 1. I'll explain why I'm putting the 1 in there in a second. Go back to vars, option 5, select 3. X bar minus 1s. All right. So that's going to give us the low bound, and hit enter. Now, the 1 bar stats had to happen first. All right. So let's make a note of this. So what did I do here? I did 1 bar stats. Then I did, in my home screen, vars, statistics, 2, then 3. Those are the 2 things that I needed. All right, that gave me X bar minus 1s. All right, which amounted to 16.686 approximately. All right. One good feature, I mean, the calculator doesn't have a copy paste or undo, redo kind of thing. Well, it does have redo. It has recall. And that's what we're going to do here. If you have either a TI-84 or a TI-83, it's the same approach, which is good. Second, enter brings up the very last thing that you did. If you have a TI-84, you could actually just hit the up arrow and hover over the thing that you want and hit enter. But second enter, I think, is cleaner. Then hit the back arrow, change the minus to a plus. So that pain in the ass step of going into the var statistics, it only had to happen for the first calculation, because now I'm just working off of previous calculations. So X bar plus 1s is approximately 20.973. All right. So the question becomes, I don't know if it's is or are. R probably, right? R, 68% of the data. Is 68% of the data? Which one is it? Is. See, that's what I was telling you before. It's approximately 68% of the data. Between 16.686 and 20.973. If the answer is yes, we have more work to do. If the answer is no, then we're done with the problem and it's not a normal distribution. All right, so we're rooting for no. Unless we're doing our own statistical analysis, then we're rooting for yes, because a lot of things are inconclusive unless it's normal. All right, so what I'm going to do is look at my X list and identify any values that fall between 16.686 and 20.973. 14 is not in that interval. 16 is not in that interval, but just barely. 18 is. 20 is, but nothing else is. All right, so I have 14 plus 13 values that fall in the interval that I'm looking for. Because remember, the frequency tells us the number of times a value occurs. 18 occurs 14 times, 20 occurs 13 times. That's a total of 27 values. All right, we have 41 values overall. All right, that's what we would get if we added up all our frequencies. But also, I didn't add up all the frequencies. I just remembered when I did my display, I didn't snip it in here, but I remember it saying 41 for n. So 27 out of 41. I don't want to mess up my calculator's mojo here, so I'll just do it on my phone. 27 out of 41, about 66. It's like right on the borderline, though. It's like a very, very iffy number. So 0.659. If you were actually to go by the letter of the law here, I'm saying 2 percentage points within that 68%. Well, it's not quite 66, but it is kind of close enough, right? So it's a judgment call at that point. All right, so we're gonna go with it. because we're going to assume that this is about 66. But you would not be wrong if you were to say it's not 66%, so the test fails. It's not a normal distribution, right? But we're gonna go with 66%. So we give it a check mark because it satisfies the condition. It's within 2 percentage points, just ever so slightly out of that interval, but we'll accept it, right? So I need x bar minus 2s and x bar plus 2s. Much easier calculations now because all I have to do is second enter. Change the +1 into a -2 and hit enter. Second enter. Change what you need to change. So we got 14.542. And 23.117 less. All right. So again, it's a question. Is about 95% between those two numbers. And again, it requires us to go back to the data set. Is about 95% between 14.542 and 23.117. Well, let's investigate. We'll go with a green highlighter right now. So 14 doesn't make the cut, right? Just shy. 16's in. 18's in. 20 and 22 are in. But 24 is a little too big. Right? So the 7 16s will count, the 14 18s, the 13 20s, and the 5 22s, which really just amounts to an additional 12 values beyond the 27 I had before. So I just need whatever this percentage is to be around 95%, so between 93 and 97. It's 95.1%, so yeah, it's 0.951. So it's approximately 95%. So we were on the fence with one standard deviation, but the 2 standard deviations looks pretty good. So now I'm kind of leaning towards normal distribution. Right. The last calculation would be x bar minus 3s and x bar plus 3s. Again, second enter, it's the name of the game. So we're looking at 12.398 and 25.268. All right, so is about 99.7% of the data between these two numbers. Right, and so you look at the data set, every single value is in between those two numbers, right? Everything's bigger than 12 and change, and everything's less than 25 and change. So that's 41 out of 41, which is equal to 100%. So that gets a check mark because that's only 0.3 away from 99.7. So therefore, 3 dots in the form of a triangle is an abbreviation for therefore. You don't have to use it, but it's only 3 dots. Therefore has, what, 8 letters? That sucks. So therefore, it's approximately normal distribution. All right, so normal distribution usually means something along the lines of a bell-shaped curve, although not all bell-shaped curves are normal. Right, it has to have a particular shape. You could have skewed distributions, which are pretty much what they sound like, just anything that's not symmetric. Right, so normal would be, that's my attempt at normal. So not skewed, something like that. That was shaping up to be way too normal. Oh no. Thank you, whoever invented undo. So it's kind of offset, not multimodal, which is something that would have more than one hump. That's trimodal. You could have bimodal. You know, anything that's got more than one hump in the graph is going to be something that's not unimodal. Unimodal is a requirement for something that's normal. All right. Standard deviation